In the previous video, I stated and proved the Bogolubov lemma, which is a very important tool in additive combinatorics. And I said that one of the things that we were aiming for was to understand the structure of sets that have small subset. And now, in this video, it should be rather a sort of fun video because we're going to have a big payoff for a lot of the results that we've proved in the course so far. We're going to have an argument that's quite short, but it puts together a whole lot of results that each required separate proofs. I'll say a little bit more about where these ideas came from, maybe as I go along. But I think I'll just get started now. And here's my bit of screen share. So what are we going to do? We're going to start with a set A, which will be mainly in this video a subset of fp to the n. And as I said last time, our aim is to show that if a plus a has size at most c times the size of a, then we can find some subspace x such that a is a subset of x and the size of x is not too much bigger than the size of a, and the idea is that c dash should depend only on c. I'll state that properly later on, and it will turn out that a lot of the argument will carry over to subsets of z. We just have to say slightly different things in various different places, but I think for the moment I'll just state it only, or I'll do it just for subspaces of fp to the capital N. So this x was a subspace. I didn't write that, but that's important. There's a little extra tool that we're going to need, and it's called Ruzsa covering lemma. So let G be an abelian group, and let A and B be finite subsets of G. Then there is a set K of size at most the size of A plus B divided by the size of B, such that A is a subset of K plus B minus B. Now I just want to, before I go ahead and prove it, let me just say a little bit about what that's actually saying. So the main situation in which we want to apply this result is going to be when this ratio is not too big. In that case, that'll tell us that the set K is not too big. And if the set K is not too big, what this is saying is that say K has size little k, then that's saying that A can be covered by little k translates of B minus B. So in the sort of qualitative terms, if that ratio is not too big, then you can cover A with not very many translates of B minus B. The proof is very simple, and actually, although it's called the Ruzsa covering lemma, essentially this argument had been around for quite a long time. It's well known in the geometry of numbers, but maybe it's a slightly more general formulation of the argument. And the idea is, all you do, once you've written down the first line of the proof, the rest just writes itself. So the first line of the proof is let k equals a1 up to ak be a maximal subset of A with the property that the sets AI plus B are disjoint. So the way I think of this is finding a small covering is sort of going to be equivalent to, or very closely related to finding a large separated subset, where here our notion of separation is that these sets are disjoint. So let's first check that A really is contained in K plus B minus B, which is almost trivial. So if A belongs to A, then we can't add it to K, so that implies that there exists I such that A plus B is not disjoint from AI plus B. If that were not the case, I would just be able to add A in to this set, and that would contradict the maximality, which is equivalent, or equivalently, so this tells us that we can find B1 and B2 such that A plus B1 equals AI plus B2, and therefore A equals AI plus B1 minus B2. So equivalently, A belongs to the set AI plus B minus B. So conversely, if A belongs to this set, then we can find B1 and B2 such that A is in AI plus B1, or A equals AI plus B1 minus B2, and then we get A plus B2 equals AI plus B1. And if we get this, so that's a simple equivalence. So therefore, A was arbitrary, so therefore A really is contained in K plus B minus B. And the only other thing to do is to check that K isn't too big. So, but also the size of K times the size of B equals the size of K plus B. That's because all the sets AI plus B are disjoint, and there are K of them, and so therefore the set K plus B just has size little k times B here. But K plus B obviously has size at most the size of A plus B, and therefore the size of K is at most A plus B over the size of B. So that's the Ruzsa covering lemma, and I think now we're ready to have a formal statement of the main result of this video. So I'm calling it Freiman's theorem for subsets of fp to the n, but that's a slightly misleading thing to call it. So let me just quickly say the story. The reason it's misleading is that this is a result of Imre Ruzsa, but the proof I'm going to give is not the proof that Ruzsa gave, but it's a very close, a very small adaptation of a proof that Ruzsa did give for Freiman's theorem for subsets of Z. Freiman gave a much more complicated proof, and in fact it was so much more complicated that for a long time it wasn't absolutely clear that it was correct, although eventually it became clear that because a mathematician called Yuri Bilu came up with a sort of rewriting of Freiman's proof that used essentially the same ideas and established that Freiman's approach genuinely did work. But Ruzsa's proof is very much more conceptual and has introduced a whole lot of ideas into the subject that have been extremely useful in many places, rather more than Freiman's proof. So what does it say? It says, let A be a subset of fp to the n, and suppose that the sum set is not too big, i.e. it is at most a constant times the size of the set itself, then there is a subspace x of fp to the n such that I'm more or less saying the same thing as before. So A is a subset of X, and the size of X is less than or equal to C dashed times the size of A, where C dashed depends only on C. I'm not going to give you the best known dependence of C dashed on C. I'm just going to get some sort of dependence. It'll actually be doubly exponential, and that can be improved quite a bit. Although, yeah, okay, so so as I say, we're just going to string together a whole lot of results that we've already seen, and the first one of those will be Plunnicus theorem. So by Plunnicus theorem, the size of 8a minus 8a, that turns out to be a convenient number to choose, this 8, as you'll see why in a moment. That has size at most c to the 16 times the size of a. Let's get a fresh sheet, so to speak. Next step, by Ruzsa's embedding lemma. Oh, by the way, I didn't say that this C dash doesn't just, I mean, it also depends on P, but I was regarding P as a fixed small prime number. But if P starts to get big, then the P dependence makes a difference, and we'll see what that comes in a moment. So by Ruzsa's embedding lemma, A is isomorphic of order 8 to a subset A1 of fp to the little n, where p to the n is less than or equal to, I think I can even say less than from what I did before, but let's just say less than or equal to, because I don't really mind about that. And I want to have a constant out here, so it is at most p times c to the 16 times the size of a. So the idea was that we could get a proof with c to the 16 if only it were the case that c to the 16 times the size of a were always guaranteed to be a power of p, but otherwise we might have to multiply by up to p. Next step. If I set g to be fp to the n, I can apply Bogolyubov's lemma. So by Bogolyubov's lemma. So what we're doing here, let me just say what we get out of Bogolyubov's lemma. 2a1 minus 2a1 contains a Bohr set b k a quarter with k less than or equal to 1 over the square of the density of A1. Now, what is the density of A1 inside fp to the n? Well, if we look here, we see that it is at least 1 over this thing here. And so we're taking 1 over this thing and squaring it. And so we end up with p squared times c to the 32. So A has, so the size of A is the same as the size of A1. So what I've just said, the alpha that I'm sticking into Bogoliubov's lemma is equal to p to the minus 1, c to the minus 16. Or it's got density at least that big anyway. Now, we also get that the Bohr set BK a quarter contains the Bohr set BK, let's say 1 over 2p, which I just chose to be less than 1 over p, which is a subspace of codimension. We saw this, I think, in the last lecture, maybe in the last video, maybe the one before, of codimension at most p squared c to the 32. So now we've got that 2a1 minus 2a1 contains a fairly large subspace. And what we need to do is somehow get to A1, to A being contained in a small subspace. But we've got the tools to do that. So it follows that 2a minus 2a contains a set isomorphic to such a subspace. And it's easy to see. So just put it therefore. So of dimension at least n minus p squared c to the 32. I think I'd like to be able to say that. So I'm going to leave this as an exercise for you to do on the example sheet because it's quite a good exercise. So it's an exercise to show, I have forgotten to make a very important remark, which explains why we need the 8. So all this is correct, but I said this just a little bit too fast. So we know that A1 is 8 isomorphic to A. It follows that 2A1 minus 2A1 is 2 isomorphic to 2A minus 2A. And that was another statement amongst the various properties of Freiman homomorphisms, was that if you've got a K R plus S isomorphism between sets A and B, then you get a K isomorphism between RA minus SA and RB minus SB, and this is a special case of that fact. And that I didn't prove, but I, again, was leaving that as an exercise. So we get from, so we chose 8 so that this set would be 2 isomorphic to this set. So it's an easy exercise to show that a set 2 isomorphic to a subspace is a subspace. So conclusion is that 2a minus 2a contains a subspace of dimension at least n minus p squared c to the 32, and so it has size at least p to the n minus p squared c to the 32, and we know that p to the n is less than or equal to p to the 6 times c to the 16 times times the size of A, so that's less than or equal to p times c to the 16 times the size of a, greater than or equal to, I need to bound in the other direction. So p to the n is greater than or equal to the size of a. So it is greater than or equal to p to the minus p squared c to the 32 times the size of a. And the key point is that this depends only on c and also p. And now, so we've got 2a minus 2a contains a subspace, but we want a to be contained inside a subspace. There's a very natural idea to use for that, which is the Ruzsa covering lemma. So let's call this subspace V by Ruzsa's covering lemma. There exists k of size, so it's not the same as the k up here. Should I give it another name? Yeah, I better do. I'll call it L. So there exists L of size at most a plus v over v, such that a is contained in L plus v. Now, why did I say v and not v minus v? It's because v is a subspace, and so v minus v is the same as v. And finally, but L plus v is contained in a subspace of size at most. So in the worst case, L is linearly independent, or L inside the quotient space where you quotient up by v. In the worst case, you add the size of L dimensions when you do that. So at most p to the L times the size of v, which is less than or equal to p to the L times 2a minus 2a, so that's c to the 4th times the size of a by Plinico's theorem. And so what do we know about L? L has size at most a plus v, but v was contained in 2a minus 2a, so at most the size of a plus 2a minus 2a over the size of v, which is less than or equal to, so this thing has size at most c to the 5 times the size of a by Plinico's theorem. I won't write that size of a because I'm about to cancel it out by this, because the size of v was at least this, so we then multiply by p to the p squared c to the 32. And so putting all that together, so a is contained in a subspace of size at most. Let's write down the full gory detail. P to the c to the 5 times p to the p squared c to the 32 times c to the 4th times the size of a. So in particular, it is a constant times the size of a, where that constant depends only on c and p. As I say, there are various improvements possible here. So a fairly straightforward argument, which I'm not going to give in this course, although I might put it on the sheet with a suitable hint, allows you to reduce this double exponential in C to a single exponential. That's an argument of Mei-Chu Chang. And so that's a sort of nice observation that allows you to do the argument more efficiently. But something that goes a bit deeper is an argument of Tom Sanders, who managed to find a very considerable improvement to the Bogoliubov lemma. So the main reason that you get some sort of exponential dependence here is that the dimension of the subspace that you get out of, or the codimension rather, of the subspace that you get out of the Bogoliubov lemma is this alpha to the -2, and in particular it depends like a power on the density alpha. And Tom Sanders managed to come up with a different argument that's quite a bit more, I mean, much less obvious than the one I've shown you, that gets you a bound that's of the form log 1 over alpha to some fixed power, t or something. And armed with that, you get you end up with a polylogarithmic dependence of this constant on C, where polylogarithmic, that just means a function of the form fx equals e to the log x to some constant, which is it's sort of only just worse than polynomial. If theta is 1, and you put just a linear function of log x, then you get a polynomial. And so if theta is bigger, these functions are regarded as just a bit worse than polynomial. And in particular, much better than exponential. But that's a whole other story. I think I won't write things down, although I have in the notes, but I just want to go back through here and just comment verbally on what happens if A is not a subset of fp to the n, but a subset of z. So let's just go through and see what breaks down and what doesn't. So the Plüniker step is identical. Ruzsa's embedding lemma is not identical, but it's pretty close. So what we get, we have to pass to a subset of A instead of taking A itself. So the subset will have the size of A divided by 8. That's what came out of the embedding lemma for subsets of Z. And then it'll be isomorphic of order 8, not to a subset of fp to the n, but subset of a cyclic group. And the cyclic group will not be too much larger than the size of A. Now that's put us in a situation where we can apply Bogoliubov's lemma again, because we've managed to show, and this was what Ruzsa, the whole idea of his proof of Freiman's theorem. So we've managed to show that a large part of A is isomorphic to a dense subset of some cyclic group. And dense subsets of abelian groups, finite abelian groups, are ones to which we can apply Bogoliubov's lemma. So we apply Bogoliubov's lemma and we obtain a Bohr set. Now we can't just sort of look at a Bohr set and say, oh, it's a subspace or a subgroup or something like that, because a cyclic group, especially if it's got prime order, will not have very many subgroups. It'll only have trivial ones in that case. So that forces us actually to think a little bit more about what Bohr sets actually look like in that case, and that I'm going to do a bit of that in the next video, but for now let's just say that 2a1 minus 2a1 will contain a pretty large Bohr set. That's another thing. It'll contain a Bohr set where this k is small, i.e. the dimension of the Bohr set is not too large, and the width is reasonably large. So I just said that means the Bohr set is pretty large, but there's a lemma needed there. You need to prove that if this set is not too large and this width is not too small, then the Bohr set has reasonably large cardinality. It's not a very difficult pigeonhole type argument, but it needs to be done. And so we get that 2a1 minus 2a1 contains a largish Bohr set, and therefore 2a minus 2a, which is 2 isomorphic to 2a1 minus 2a1, just as before, contains a set that's isomorphic to a Bohr set, not a subspace, but a Bohr set. So we need to show that the Bohr set has some sort of structure that will carry over when you apply a two isomorphism. So that's again something I'm going to discuss in the next video. So the next video is going to be mainly devoted to what can we say about Bohr sets, and when we apply this argument, why is it of any interest at all to learn that 2a minus 2a has a subset that's isomorphic to a Bohr set. But anyway, it does, and then by Ruzsa's covering lemma, we'll be able to get that A is a subset of a small set plus Bohr set minus Bohr set, and Bohr sets, you can no longer say that B minus B is equal to B, but anyway, it turns out that if B is a Bohr set or isomorphic to a Bohr set, then B minus B has still quite a nice structure. And so we get that that the set A is contained in a set it's contained in a small number of translates of a highly structured set. And I haven't justified that a Bohr set minus a Bohr set is a highly structured set, but it turns out to be the case. And one can go further than that, or further than I'm going to go. I will say a few results about Bohr sets, and maybe I will just state, without proof, a further result about Bohr sets that enables one to arrive at the statement of Freiman's theorem as it is usually given. But that's all for the next video. I've just given you a little foretaste of what's to come. But I will stop there for now.